All right, I'm gonna get started. Everybody, can you hear me over there, a mile away? Okay, cool. I've never worked a room like horizontally before, so bear with me. This is the life of a system call why containers are so hard to secure. I'm just going to give you some of my takeaways up front, or the stuff we're going to talk about, so I don't want to trap you in this room. Containers are not a security boundary, but can they be, is the question that I'm kind of trying to answer. I've worked for a bunch of years now trying to secure containers, and then customers will also ask me, hey, can you turn it into a sandbox? And we'll talk about like what actually has to go into that. And why are all these customers asking me to build remote code execution as a services, and why are we using Kubernetes to do that stuff? We'll talk about system call filtering with like seccomp and hypervisor stuff, and how to do it correctly, and how to turn a container into a sandbox for some definition. So for security architects, if you're building stuff, we'll talk about like here's how you can do this stuff. For pen testers, we can show you like here's how you can do it wrong so you can exploit it. And if you're just trying to like run a Kubernetes cluster and keep the lights on, like I'm with you. Like that's kind of what most of us are doing. So, how many people have heard this in some way, shape, or form? Like containers are not a security boundary. We've kind of like we've recited it, right? Like we just go, containers are not a security boundary. Containers are not a security boundary. We can't trust it, and it's like this. You know, like a pool lane that you have to swim in, like nobody's stopping you from breaking out of it. Whoops. To answer the question, I'm going to set this up with these little anthropomorphic metaphors throughout this presentation to make some like the esoteric topics slightly more interesting, at least that's the hope. If you think of an application, it's kind of like a factory that has access to memory and storage, and like inside the factory it's doing a bunch of stuff. But the things that are interacting outside of the factory to the rest of the operating system are like the system calls, so the open and the write stuff. So you think of like an application, it's just a process that's running. If you have like a hello world application, you statically compile this. The factory is going to have some like system calls that go back and forth. So it's like, in reality, like here's the Linux kernel, here's your process. It's constantly interacting with the Linux kernel to get your process done, whatever it needs to do. So these processes are made up, and this is just normal process stuff, of executable code, like memory mapping, some file descriptors, and like these system calls that will interact with the Linux kernel. Because when you think about it, like at the processor level, the CPU doesn't understand what a file system is, or like what a file is. These are all metaphors that are abstracted by the kernel. So if we want to use any of those things, like opening a file, we have to use system calls to talk to the kernel and say, please go figure out what a file is and open it. So then what's a container? Container's like this factory that's like, I don't know, it's got guardrails around it, but we still have the same idea of like the system calls need to come in and out of the container. So we can't say it's completely container isolated, it's not restricted. We still have stuff that comes out of the container and interacts with the rest of the kernel. Because at the end of the day, containers are just these filtered views, right? Like each of these two processes, I got 2 instances of Nginx out there. These are just things that the Linux kernel looks at as 2 separate processes, whether or not they're in namespaces, whether or not they're just running on the host. Those are just labels for the Linux kernel. So from the kernel perspective, a container is just a process that happens to be running on the host, and you get a couple of extra like things on it, like this is where we get into kernel namespace and the C group stuff and all the things you can kind of bolt on. But those are mostly like, if anybody's worked in SE Linux, kind of like the idea of like labels, right? You just attach some metadata to the process, and now we call it kind of like isolate. So what's a sandbox? I'm interested in other people's perspectives. Somebody tell me, I'll take wrong answers too. What is a sandbox or what is not a sandbox?
A testing environment.
What's that?
A testing environment.
Testing environment, that is a very good answer. That is one type of sandbox. Yep, good. So trying to get into the isolation world, least amount of damage. Somebody say what is not a sandbox? Yeah.
I'll just say a sandbox could be like a controlled space where you're free to basically test things and troubleshoot.
Yep.
Different.
Yeah, and in a lot of ways, that's how sandboxes started. Like the original concept of sandbox, like a lot of things in InfoSec was started in the military, where they literally would bring a box of sand and like little toy, tanks. I'm just imagining like, oh, where should we put the bombs today? And you kind of like line them up and then things. So this was a sandbox, and this matches kind of what your definitions were talking about, where it's just like a play area, mess around with stuff. Salespeople do sandboxes all the time. But the sandbox I'm talking about is more like the one you're talking about. I'm interested in It's more like a tool that helps guarantee that something inside of it, whatever it is, can't break out and get to the underlying host. So you can imagine like malware sandbox. You've got malware, you want to download it. You're not going to just run it on your host. You don't know how it's going to affect stuff, so you put it in whatever a sandbox is. And that word has been used a whole bunch of different ways. There's like the Chrome sandbox, there's virtual machines, which are they a sandbox, there's gvisor, there's Kata, there's a bunch of things that could be kind of called sandbox because it meets this definition. But also a container kind of looks like a sandbox, right? If I just take that definition, I go, it's something that confines you and prevents you from doing anything else. The container is attempting to do that, right? But we don't really trust it. So what would it take to turn a container into a sandbox? And that's kind of the things we're going to be talking about. eBPF, seccomp BPF, emulation, virtualization, these are all kind of some options. So to back up, my name is Mark Manning. I go by Anti-Tree on the interwebs and stuff. I used to work for NCC Group where I was running their container practice, which just means anywhere you crammed a container, we could do a review of it, and some people in the crowd know how this works better than others. There'd be weird places where containers existed in firewalls and in cars, and whatever it was, we would kind of like do an assessment of it. I worked at Snowflake, where I was trying to build their Java UDF thing, and the Python UDF thing was like isolating with like a ptrace supervisor. You don't need to know about any of these words, but just I was attempting to build RC as a service, and that's kind of what I've been doing the last like few years of my career. I spun off into a consulting company where I'm focusing on doing a bunch of gvisor and Kata and like building these RC as a service stuff, because there's more and more customers that are demanding it. Even though I tell them like, hey, don't do this, it's probably not the best idea. I can still help you figure out the best way to do it. Today, I work at Chainguard, and we secure software supply chain security stuff through secure containers, and I'm working on like some of the secure build stuff. When we think about like secure build, it's kind of RC as a service, right? It's like somebody else's code running in your environment. So I spent most of my career as a breaker. In the last 4 years, mostly trying to be a builder or like aspirational builder. I tried to do the math on it, like more than 100 different environments doing penetration tests on quote-unquote container environments in some way, shape, or form. I've worked with 6 teams building these RC as a service things. I accidentally got a couple of patents. You know, if anybody works for some of these companies, you know how kind of like patents just fall in your lap sometimes. I started BSides Rochester. I run Rochester 2600. Anybody from Rochester in here? Okay, nice, represent. And over 9,000 is the amount of times that people have asked me, like, why do I keep working on Kubernetes? So we're going to talk about system calls, talk about hypervisors, we'll talk about seccomp, and then I'm going to show you some new tools that I think are interesting. So how do containers actually work? We probably go like, hey, containers, a bunch of system calls that just like execute some stuff, and like I run that Docker command, it just works, right? When I say system calls, I'm making these little anthropomorphic system calls because every single system call has like a personality, and everything has a different purpose, and they have these different parameters. But the simple thing to think about these are just like the API mechanism for talking to the Linux kernel. We don't need to like overcomplicate it. I made them like anthropomorphic and like friendly, just because like they feel like more fun to talk about. Like nobody really wants to talk about clone and execb and just kind of esoteric. But each one of these is important, and each one of these has a different impact. Each one of these are not necessarily nefarious, and each one of them has a different purpose. But we can use different system calls for different purposes, and attackers can use them too. So like the ptrace system call isn't inherently evil. It's just that if you allow ptrace in production, it's probably going to damage you, or it's going to cause some problems for you, because you can hook other processes, you can hook other system calls and tell it to do different stuff. So we don't want to run ptrace in production. And similarly, like write commands, you go, write's not nefarious, there's nothing really wrong with it. I need to write to displays, I need to write to different outputs. But if you're writing something malicious, or if you're writing, an attacker can use write in the same way that a good person can, right? So there's different kind of perspectives. And then there's system calls that operate in different modes. eBPF, anybody heard of eBPF? I'm just seeing if you're awake. Everybody must have heard of eBPF, okay.
Imagine I could.
You have not? Okay. eBPF is an underlying technology that's designed to work in a couple of different ways. to either do like networking controls or do like low-level kernel system monitoring. So I like to think about it in like these two modes. Like one's just watching stuff in the kernel as it runs. The other one's more like policing, where you go, I'm going to block a certain system call if I don't like it. I'm going to watch what's going on in the kernel, and I'm going to restrict things. So like I said, this is how a kernel, this is how a container is created, right? You start Docker, run the image, some magic happens, and poof, container. And if you get this joke on the left, then I think we can be friends. If not, that's okay too, because it's pretty hyper-specific. So let's look at.
They're supposed to be clones, but they're getting older.
Well, they're getting older. It's the parent-child relationship. It's the processes. What I was trying to say.
What you're right foundation.
Oh, I like that too. Oh, I didn't realize this was so deep. I'm a pretty deep guy. I don't know.
You're getting deeper.
So let's look at actually how a container is created. I spent a bunch of time actually doing the analysis on like at the system call level what a container looks like. And you don't need to memorize this, but it is a great interview question that I've actually had a couple times. Of like, how does a container work? How do you start a container? So if you imagine I'm starting Docker, Podman, or even like the Kubernetes, it interfaces with containerd through a gRPC call, and it just says, hey, start container or run container. It makes a fork and exec, which is a common thing that happens in processes. Let's just make like a separate process underneath my main one. And I'm going to run this containerd shim process, and this is a completely different binary. This containerd shim process's main purpose is to manage all of the containers that are running and all the container processes that are running. So when I run containerd, I'm going to do a fork exec, and when I'm running the shim, I'm going to do another fork exec to run the runc process. And if this feels complicated, it's because it actually is. Runc is the part that does all the security. So I want to be clear, like kubelet hasn't done anything, containerd hasn't done anything, and shim hasn't done anything. This is the part that does all of the containerization stuff, where you do the clone operation, which takes a clone of the original process and all the memory mappings, and it goes into, I'm making a new network namespace, some new process namespace. So all the stuff that we think about with like containers and namespacing stuff, it's done by this runc init process. Now we haven't even talked about the thing that we want to be running, right? Like at some point we want to run our own process in this container. So this is just the setup. We now have a kind of hollowed out namespace to run our own processes in. Runc init has created that whole thing, it cloned itself, and then it gets into whatever binary that you want to do. So there's an exec in here that says I'm going to do some hello world, command or process. What I find is interesting is like, okay, you go like, okay, this is complicated, but who cares? This is the important part for security in a lot of ways. The runc init process kills itself. After it creates the shell for the container, it doesn't keep going, it doesn't maintain in the background or anything like that. It kills itself. And now the hello world process, it actually abandons the child and redirects it back to the grandfather process of the containerd shim. So one of the security benefits of doing this is there's a bunch of attack vectors of being able to go back up through, when you think about like what is PID1 and some of the UID management stuff that they do. This blocks out a whole bunch of attack vectors by doing this. So when we talk about like namespacing, like that's all cool. This is really one of the bigger security controls for containers. Okay, if you didn't catch that, it's okay. Understand it's complicated and there's system calls involved. We'll come back to that later. So still we will say containers are not a security boundary, right? But we're not really doing that classic thing of security people, right? We just go, it must be the most secure possible thing in the whole world, but in reality, containers are not always designed to be secure. When Docker was created, it was like a development tool. And I think of Docker as like having a house, and we've invited our containers over to our house, and they're our friends, and we've vetted our friends. And like they're hanging out, and like, okay, maybe they could potentially be malicious, but if they were malicious, kind of more like a dick move, as opposed to a CVE, right? If someone's dropping an ODay on your container that's running at your house, is that really a security flaw? Is that part of your threat model? Like, no, it's really not its main use case. And then you have Kubernetes, which is more interesting because we run Kubernetes in production. We have customer workloads on this thing. Kubernetes is kind of like an apartment complex that you own, where you vetted the things that are running there. You go, yeah, I'm running Alpine, I'm running Nginx, cool. But if anything goes rogue in the middle of the process, there's nothing stopping that. if you've got a bunch of neighbors that like you did a background check on, like cool, this family's in there, but then like one neighbor's fighting another neighbor, like what are you supposed to do? Right? You just kind of go kick them out after they've done something bad. And the real risk here is less about like breaking out of containers, like someone knocking down the wall. It's more, you know, unless you live next to like Ted Bundy, like bowling heads in the next apartment, right? If you don't know that reference, I got a documentation. The real risk is like noisy neighbor stuff. Where you go, this metaphor works two ways. In our apartment complex, there's some directors playing music too loud. In the real world, it's like I'm consuming too many resources, or you know, taking up logs and all. But this is what I really want to talk about. The RC is a service scenario of Kubernetes, where you go, this is more like a prison. I know they're going to be nefarious, or at least I have no control over who's going to show up. So I need to lock them down, confine them, restrict the resources that they have access to. They don't do mounts, they don't do everything, and we're going to, you know, hire prison guards to make sure like everything is cool. And in the same way, if anybody remembers Shawshank Redemption, if you have a spoon, you want to dig through the wall, we can imagine that like with enough effort and enough time, somebody like an APT, a nation state, can probably dig their way through one of these containers and break out of the containers, but we're hoping that like after they get out of the sewer, we have other controls in place like BPF to kind of monitor some of the bad actors that are happening. So fine, how do we actually secure all these dangerous containers, which is what I mostly want to talk about. The first one is hypervisors. And the premise here is like, you know, I used to do talks that would start off with containers are not virtual machines. And like, just because it seemed like they kind of were, and like it didn't make sense at the time. And I'd be like, no, containers are not virtual machines. But now we're kind of back saying like, well, some of them are now. We now support different types of things like kata. So if you have bare metal, like you imagine you've got hardware, you've got a kernel, you've got binaries and libraries, and you've got a processor runtime. This is just like how computers worked in like, what, the 90s? And it's, ironically, we're coming back to this. You know, we can now buy bare metal instances on AWS. And then if we want to do a virtual machine, it's the same idea, but somebody was like, hey, can I stack more software and more fake operating systems onto my machines to optimize some of the hardware consumption? And they said, yeah, sure. So you have a base hardware, you have a hypervisor like something like ESX. Then you have kernels that go into each of the virtual machines, and this is the important piece. There's a separate kernel for each of the VMs. So when we talk about like breakouts and exploits, they have to exploit that kernel for that instance of that VM, which is what's different than a container, which is more like, okay, we got hardware, we got kernel, we have this like really light supervisor thing, and that's the containerd process. It's just watching processes, watching the containers, like are they still running or not? Should they be doing something else? And one of the other nice things about containers is when you have two instances of Nginx running, right? You would go, I don't need to have two copies of Nginx. I can just maintain the same base layers so that like my two containers can both use the same instance of the Nginx binary to load up into memory. So between these two things, one of them is a hardware-backed isolation model. Like you look at Intel VTX and all the stuff that goes to virtualization, like that is a stronger boundary that's on process to do like memory separation and process separation. Hypervisor stuff and virtual machines are a strong boundary. Let it be completely clear. This is the best option for doing any kind of sandboxing stuff. But we also have gvisor. Has anybody used gvisor? Just in like, just testing it out or anything? Okay, cool. So gvisor is like, if virtualization is actually some hardware-backed thing, gvisor is running a kernel inside of userland in like a normal program and faking all the system calls. So like, what if you could fake the kernel so that whenever I ran everything, it would go to my fake kernel. So if you exploited anything, it exploits my fake kernel. This came out of Google, and it's what Google uses for what they call Borg internally. And it's basically you can run any kind of workload that you want on any kind of environment. It doesn't need virtualization. It has a bunch of different modes that you can run it in. You can run it in virtualization mode, but it has this systrap mode. So if you've ever heard of gvisor, usually your reaction is like, oh, this thing's too slow. I'm not gonna be able to use it. But there's been an update in the last couple of years that makes it faster.
Yeah, well, you just said that you're emulating it, so I mean, the slowing comes down because you're literally streaming something off the cloud, or you're running it off of like an ISO. You're not running like the actual machine. Like sometimes VMs are slow because you're on like your home laptop or your home computer, right? Running a machine that could be in like California or something.
Yeah. So the main reason that this is like slow is because of I/O, because they have to face some of the I/O system calls.
Yeah.
So when you do a lot of like file-based stuff, it's like 3 more hops to get to the actual I/O operation that you need. But the takeaway that I want you to have is that like gvisor is good. Nobody configures gvisor. They click the button, turn on gvisor, and they go, it either works or it doesn't. But there's 132 config options that have major differences in the performance and the security of gvisor as it's running. My whole point is like, if you take nothing else away, like gvisor is a viable option for people that are in the cloud or in bare metal or wherever you want. You can run gvisor and you can tweak it, and there's a bunch of cool things that you can do. I know this because like at Snowflake, this is a thing that we were in a highly performant requirement environment, and we still were able to make it work. So which ones do you actually choose? So we've got gvisor, we've got virtual machines. Kata containers is an example of like a container runtime that's like a micro virtual machine that is a really good security performance benefit. Like this is like the best one on a big I'm going to talk about today. It works great on bare metal, but you run into problems when you have to do like nested virtualization. If you're using EC2, you need to buy like the nested virtualization extra option on EC2, and you can do it on bare metal, but that also costs more. This is like, if you have that environment, this is like point and click, I'm just going to do this, and poof, like everything's solved. gvisor is another great option. You can run it anywhere. So if you don't want to do the bare metal, you can do it on GKE. This is what GKE, Google's Kubernetes, managed Kubernetes environment, they call this shielded nodes. So you don't have to do any configuration at all. You just say, do you want shielded nodes? You click like this little radio button and you go poof. You now have like a much stronger isolation boundary. And a lot of the other tools that Google provides is using gvisor under the hood. The only warning is heavy I/O stuff. If you're doing tons of file operations, it's going to be slow. And if that doesn't matter to you, like if you're doing, like it all matters on the scale. If somebody was expecting 100 millisecond response time and now it's at like 200 millisecond, if that matters to you, then like maybe gvisor isn't going to be the best option. And the thing I'm going to come back to more is seccomp. Seccomp VPF is kind of like the de facto, if you want to secure your Kubernetes cluster, this is what you're supposed to do. And I'm going to tell you about like, some of the sharp edges here. The amount of effort to get this done is high in my opinion. The performance though is the best. So if you're really in a performance sensitive environment, or if you don't want to deal with virtualization and like all this other stuff, Seccomp VPF gives you the best bang for the buck if you can invest the time to do it. It's just highly prone to misconfiguration. One more thing to circle back on gvisor. gvisor has these different modes, and when we say gvisor, we're actually thinking about different modes of gvisor. Right now, like I said, people just install gvisor, they go, gvisor, it's a binary question, yes or no. In reality, you can run it in paravirtual, you can run it as a virtual machine, you can run it with its own network sandbox, which you probably never heard of before. Who would need that? But like Google's sandbox technology is they found out that the Linux kernel in the past like 10 years, there's been 2 of these, where the Linux kernel had a vulnerability in the way that it was parsing packets. And they said, well, we can never have this vulnerability ever again. So they built an entire dedicated network stack, just sandbox anything from the TCP. We'll just run this thing. Very cool property. You can also run it in like non-root mode, so the entire thing can just be run as a non-root user. There is a feature there if anybody's interested, and you can talk to me after about some of the details. So let's talk about Seccomp VPF, because this is something that I've had tons of customers say, well, this is the solution for Kubernetes. I think if you take like one of the Kubernetes exams, they tell you this is how you secure Kubernetes. So let's go into some of the details of the stuff they're not really telling you. Because this is the idea of like, hey, I want you to protect the kernel integrity at all costs, but not that much cost, right? It's like, I don't want you actually to have to install anything or buy anything. I just want you to tweak what you have. So back to the kernel, the Linux namespacing problem with containers is it's just this. It's just that in virtual machines, I was telling you, there's a separate kernel for every single virtual machine. For containers, it's one kernel, it's shared across everybody, and the shared kernel problem is the kind of the main premise of like everybody saying containers can never be secure, containers are not a security boundary. So let's like lean into a little bit more. How could we secure it? Because we know that every container, you know, that factory metaphor I was trying to say, every container has these system calls that are going in and out of it all the time. Exec v, read, accept, all these different things that would be non-nefarious, but like just part of normal operations. But this also implies that every attack, every breakout uses these same system calls. So we end up coming to this conclusion of, hey, if I can block the system calls, I can block the attack. Or at least it limits the attack surface of like the potential even like ODAs that are coming out. If I can restrict what my container needs to do and only confine it to that exact same. So SecComp started in 2005. It has one of the most pretentious names that I've ever heard. It stands for Secure Computing. Like in 2005, they're like, hey, we've solved it, guys. All we need is secure computing. We just need to turn this thing on. Secure Computing was created in 2005 to just limit the system calls that are allowed to go in and out of your application. And then SecComp BPF came along, and it's just to complicate everything, because we go, SecComp BPF is related to eBPF, right? Well, no, not at all. Actually, it's actually related in the same way that Java and JavaScript are related to each other. It is a BPF format, the Berkeley Packet Filter format, that SecComp BPF is in. I can probably spend a half an hour describing how stupid this is, but let's just move on. To get a SecComp profile, all you have to do is, like, if you remember that like Hello World application I'll show you in a second, you just modify your own code and kind of import the libsecconf stuff and say, here's the filters of system calls that I want to run. What changed is Docker came around and they're like, hey, I'm managing the processes. I don't need to care about the programs. I don't need to change the code itself to do SecComp profiles. I can do like the entire outside of it. I can do the container part as a SecComp profile. Was this a good idea? So here's our Hello World program. And here's an example of, we just make like a, you know, a SecComp allow list. So here's a couple of system calls that we want in there. And it just like loads up. It just loads the system call, or the SecComp filter. Now, whenever this process is running, it will be confined to only run those two system calls. Now, whether or not that causes your application to crash is up to you. Docker was like, you know what, I like that idea, but you know what it needs is more JSON. So they abstracted SecComp away, and they said, we're going to make a JSON format for you that does the exact same thing as what we're just doing in C. And you can kind of think of this as like firewall rules, right? You can see like there's a default rule set that says either allow or deny, and then you put in a bunch of rules underneath it that says, okay, maybe I'll do like the default allow everything except for this, or default deny except for these specific ones. And you can get into like very complicated conditions. You can say, I want to log the open-ax system call, but only when the third argument is the number 4, just as an example. So you can get super complicated. It doesn't need to be this binary thing of like, I'm going to allow the system call, I'm not going to allow the system call. You can say, I'm going to allow the system call in this case, and you can kind of confine it that way. So if I said we needed to do all these system calls, we needed to build a profile for our SecComp thing, how do we build a list of all the system calls that come out of a container? Does anybody have any ideas before I tell you? What would you use to find system calls for your application? Any
ptrace?
Ptrace? Yeah, we could do that.
strace?
strace. Be more specific. Yeah, that's good. Like this is like a scenario that's been around for a while. Oh, I'll get to the tools in a second. But it is going to be like strace and ptrace. Just dump the list of system calls that come out. So years ago, I had a company come to me and say, hey, we've got this complicated thing. I've got users that want to upload an image of their own avatar. Like every time they upload an image, I want to just resize it, or I want to like tag it with like a different, political thing that I support at that time. And I went to the internet and found this really cool tool called ImageMagick. And they appropriately were, sometimes when I say ImageMagick, people go, whoa, because everybody kind of knows that it's impossible to secure ImageMagick because of all the different file formats that it needs to parse. So this customer also knew that too, and they were like, listen, I don't think I'll ever be able to secure ImageMagick, but I want you to build a SecComp profile that just restricts it to only the thing it needs to do. Don't worry about the parsing stuff and prevent any kind of container breakouts. So which system calls do we get? We can write that hello world program or which system calls does that actually translate to? How do you know you've got them all? Let's exercise an application. In the same way, if anybody does fuzzing, it's the same idea where we just want to navigate every single branch and then see if we can't knock out the system calls from executing. So Josh mentioned strace, like that's the classic one that's been around since the 90s, right? Just strace, a binary, dumps out all the system calls that you need. There's a tool that's now been kind of archived, but it's still interesting how they were trying to work it, called Zaz. No one's used Zaz before, right? Like I just found this thing. This is a tool that will attempt to spin up your application like your Alpine image, and it'll just, whatever stuff you need to do in it, but it also lets you feed it like random things for it to do. So if you want to exercise the whole application, you can kind of run the web application, visit the web application, make it do whatever it needs to do, and then it'll automatically generate these seccomp profiles for you. The official way, and what you've probably seen in like any of the CKA exams, is this OCI seccomp BPF hook. Just rolls off your tongue. Right? You install this, and now you can annotate your Kubernetes environment or your Docker environment. It just says something like trace syscall, and then output the seccomp profile that you want to store, and done. So all this is supposed to be generating a seccomp JSON profile that you can use on Docker, on Kubernetes, on Podman. It's all standard. My favorite tool is Inspector Gadget, which is you can install, if you haven't ever installed kubectl crew, you can just do crew install gadget, and it'll install this BPF-based tool from the really smart people that used to be at Kimball. They're now at Microsoft. But it lets you do like background processing. Like what if you could just scan your entire Kubernetes environment and generate seccomp profiles for everything that's running? Those tools are complicated. Let me give you a really simple tactic. All you do is create a seccomp profile that says the default action is log, and then don't put any system calls in it. And all it's going to do is start spitting out all the system calls that your container uses. And you can just imagine running this in production. You just go like, whatever you're going to do in production, just do it, and then like maybe I'm going to come back in like in a week, and it should have all the system calls from that container, and then I'm just going to make a seccomp profile for those systems, right? So, sorry?
It's like auto to allow for instance.
Yeah, no, exactly. It's the exact same idea. Just like it just ends up in the actually same function as that stuff. So this is kind of how, do we feel that Kubernetes and Docker kind of go together? How many agree that like these are best buds, best friends? Like yeah, they're kind of like, yeah, they're doing stuff together. Under the hood, what Kubernetes has done is more like this. Kubernetes is now forked away from Docker completely, so Docker is like a product and a company, and they're kind of being like, oh, we've got this community thing, but like they have split apart. And this is going to be important in a minute, but I just want you to understand that like Kubernetes now runs containerd. Docker has run C under the hood, but they do dockerd, which is based on containerd, I think. So I don't know, it's complicated for Docker. Let's focus on Kubernetes, and back to our Hello World program. So Josh said, let's do strace. Let's do strace on our Hello World program. Down at the bottom, you can see it says system calls, just like a summary of what it found. 17 system calls to make just a Hello World program that just prints out. It's statically compiled. The smallest list I can imagine. Now let's do the same thing for a container. I work for Chainguard, so let's use a Chainguard container because I know it's the most micro restricted container. And then I'm just going to copy in the hello binary, and I'm going to say run the hello binary. There's nothing complicated about this thing, and I'm going to do strace in that container. What you're going to see at the bottom, I'll zoom in for you, is instead of 17, we now have 1,811 system calls. Wow. And you go like, what are all these system calls, and do I need to add all of them to my seccomp profile? I'm doing this in the wrong way on purpose to demonstrate, like, this is the important piece. Here is, I'm going to admit right up front, like, you will get the wrong answer, but let's get some interactions to see if you're still awake. A seccomp profile is applied to a process. And here's the processes that I told you were involved in containers. Who thinks that the seccomp profile is applied at like that first containerd spot? It's okay. You can just say wrong answers if you have no idea. Who thinks the seccomp profile is applied at the containerd shim spot? No, they're just some of a couple arms. Thanks. I just know you're still alive. That's good. What about the run C init process spot? That's where seccomp was provided. Sure. More hands. What about at the hello world spot? Like that's where the seccomp was provided. No. How many people just have no idea? Okay, thank you. Okay, we do have hands. Okay, I appreciate that. So here's the complex situation that we have. It's started out, if you're using Docker Community Edition, it's here, which is absolutely insane. If you do it on the outside here, you have to capture all the system calls from containerd, from containerd shim, to run C init, to hello world. So what you're going to see is there's all the system calls that you need to start up the container, include really dangerous stuff like the clone operation, unmount and unmount, all the things that are part of the container process. It goes back out here. So run C 1.2 and below, which is what Docker's using right now, it does it out here. Newer run C does this, which is do it at the container shim level. But like I said before, all of the main operations are happening at the run C init part. So it still doesn't make any sense to do it out here because you're going to be getting a whole bunch of extra unnecessary operations. As of Kubernetes, well, containerd and run C 1.3, which just came out in like the last month, they refactored this again, and now the seccomp profile is actually in a more sane place. It's at the place right after you do the clone operations I was talking about, like building the container, then it's actually applying the seccomp profile. Why am I describing that? Why does that matter? We are not comparing seccomp, like custom seccomp profiles with nothing. It's not like, well, it's better than nothing. We're actually saying there's a built-in runtime seccomp profile and SE Linux profile and AppArmor profile that's pretty good. It was built by Jess Frizzell and it hasn't been updated that much. And it's got some really smart things that it does in there. It's a pretty, like some of the system calls are dangerous, but the most dangerous ones are kind of confined to only do a specific thing. Versus if you just took that seccomp profile that I gave you with like 1,811 system calls in it, you'd be adding a whole bunch of dangerous things on here. Like why is my hello world opening a socket? Why is my hello world doing unmounts? And why can it load BPF programs? Like this is the problem of building these seccomp profiles because it's highly prone to foot shooting. So here's an example. I did all the tools that I just listed, Zaz, BPF hook, inspector gadget, and I said generate a profile. I even did Claude. I was like, I don't know, you don't even know, like, do everything with an LLM, so why not just generate one of these things? Every single one of these is different in some different way. Now, which one is more secure? Which one is actually accurate? We're gonna figure that out. So I built a new website that is just opening up today called seccompare.com. If I can figure out how to switch over to it. Let's do a demo. And we can go to the site right now if you want to play along. Imagine we've got two profiles, and I'm going to do like, here's the inspector gadget profile versus the, we'll do the Zaz one. And I want to compare these two different things. And what we're going to see is like, okay, here's a substantial difference in the amount of things that are going on over here. Let's focus this down a little bit. Let's focus on just the system calls that are the most dangerous. So one of these allows for clone. One of these completely blocks clone. We swap out for, let's do the log one, and let's just compare it to like the default for containerd. You'll see that there's a whole bunch of things that are allowed. Like these are all the dangerous ones that are being allowed over here. These are the ones that are blocked. The main problem I'm trying to draw here is we don't know all this work you put into these custom seccomp profiles. You don't know if you're actually making it less secure than the default. So this website is designed to analyze that stuff. You can upload the URLs and the images, and I'll actually even try to build them for you. So a whole bunch of dangerous, fun stuff. I've also built a tool called seccomp diff that I'm not going to really go too much into now, but the seccomp diff is designed to actually p-trace the processes as they're running in your Kubernetes environment to tell you what the seccomp profile is as it's being applied. So this one's public and you can do kind of fun stuff. So I wanted to talk about system calls today. I want to talk about hypervisors. We did some of that. We talked about seccomp, and I'm pointing out a couple new tools. And we talked about, your local environment is kind of like your house. Your Kubernetes environment is kind of like an apartment complex. And then your RC as a service is like the uncle you have in prison. The RC as a service stuff is obviously more fun. So this is in my experience. Let me just let's do a poll here. How many people are doing like normal Kubernetes of just like keep the lights on? I'm just like their environments are like I'm just running an Nginx service, right? Like it's not doing anything to come. How many people are exposed to Kubernetes like doing RC as a service and doing dangerous stuff inside of clusters? Okay, that's good. Last time I did this, it was like way too many people saying that they were doing this. Because there's this other sliver in here of like, there's a bunch of people doing that, and then there's a bunch of people not doing it correctly, where the amount of people that are doing it safely is extremely low. And it's because of this problem of seccomp and performance and all the balance that you have to do. So if I was going to summarize some of the stuff these are the main options. We can keep a container inside of a container, do the standard stuff, run your CIH benchmark tools, and just come out and says like, don't run unprivileged or run unprivileged pods. Run is non-root. Kubernetes just came out with the most recent version with user namespaces being supported. That seems crazy to me, but it's super strong security boundary if you want to turn that on. Don't do host mounts. There's a whole bunch of lists of like things not to do, but this is just standard hardening stuff. Don't mess around with seccomp. Just use the defaults. Use the one that's already there. Just turn them on. Just make sure that AppArmor, SELinux, and seccomp are turned up. Like that's kind of your baseline if you're just keeping the lights on for your Kubernetes cluster. So one of the fallacies that I try to go through is that like how useful is custom seccomp profiles, and how many times did seccomp protect us from previous exploits in Docker and Containerd or in anything? And there's only been 3 times that it protected us from the CD. That's not to say that it doesn't protect us from like other things, like other container breakout strategies, right? Like just misconfigurations, and it's still useful. I don't want the takeaway to be that seccomp bad, but like let's not overinvest in what seccomp is, and like the amount of time and effort to do it correctly is harder. So option B, if you care, if you've got RC as a service and you can pay for virtualization and you can pay for the bare metal instances, Kata containers is like a point and click virtualization container technology. You can run it in your Kubernetes clusters for that. BSides works universally. If anybody's using Google Cloud, does anybody use Google Cloud in here? Yeah, exactly. Okay, there's one. Yeah. Not many folks are. I mean, I personally use it, but like most people are on AWS or even like Azure seems to be more popular. But in gvisor, it's just point and click to turn on like shielded nodes for GCP. And something I've been working on lately is doing more QEMU for like microkernel stuff. But it's all the same thing. It's a virtualization or a strong boundary. Option C is the containers and the seccomp stuff that I've been trying to get into. Yes, you can do this. Yes, you can install Inspector Gadget. There's a operator called the seccomp operator that will, I was mentioning that like BPF has a problem of it's not enough JSON. Well, Kubernetes came along and they're like, well, your JSON doesn't have enough YAML. So it allows you to take the JSON file, convert it into a YAML object in Kubernetes. So now we're 10 layers of abstraction away from the actual assembly that's in the kernel. But you can run the seccomp operator to manage your seccomp profiles in the cluster, so you don't have to manage them on disk. So a bunch of fun details of like how to do this at scale. I've seen a couple of environments that do this. It's challenging, it's possible, especially for like super high risk stuff. But the question, and like this is a lot of often how my talks end up coming at the end, where it's like maybe not Kubernetes. It's not a popular opinion, but like why don't we step back and say like why was Kubernetes chosen in the first place? Somebody needs to convince me that an EC2 instance or like Fargate doesn't provide the same, if not better, level of security and scalability. Like it's really nice that we've got this nice little Kubernetes API, everybody uses containers, but maybe it's really not designed for the RC as a service thing. And has it become this attractive nuisance? So we said containers are not a security boundary, right? Like we've kind of validated why specifically it's not. I think there is some value in saying like it is sometimes a security boundary or some level of security improvement, like ephemeral processes that are built and destroyed all the time and that are being like isolated as a first principle is a good security process, is something that has like security benefit. But we can't say we can rely on it as much as virtual machines. But why do people keep coming in and saying like, I want to turn my Kubernetes environment into a bunch of sandboxes? And I think it's because of this. Has anybody heard of the attractive nuisance problem? It's like a legal thing. What's that? If anybody's seen there's a Curb episode about this, where it's like the scenario of you've got a pool in your backyard and it doesn't have enough fences, and like somebody breaks into your house and your land and dies in the pool because they fell in or something like that. It's your responsibility because your pool was an attractive nuisance, because it was so pretty looking and shiny looking and it looks so like fun to use. And Kubernetes is kind of like that. Like people are just looking at Kubernetes like, ooh, it's pretty and shiny. I think I want to use this thing. And they should know about the dangers. That's one of the other properties. And developers have known about the dangers of Kubernetes for years, and they still don't like they don't build in security into Kubernetes day one. They're now kind of bolting it on now. The other problem is that like if you just don't understand the risk, it becomes an attractive nuisance. And Kubernetes is so esoteric and complicated that I can only say I might know 20% how Kubernetes works, and I don't know if anybody knows completely how the whole thing works at this point. And then the lastly that makes this an attractive nuisance that's like is your now like legal responsibility is that it's easy to secure and like you could just do a couple things. And so now I've described like Kata containers and some of this point and click stuff. It makes it easy to secure. So I feel like this is what Kubernetes really is. It's like we've got AVPF to monitor the pool, we've got these containers running in the pool, but it's really just like, I don't know, body of like murder water, where like anybody can just be falling into accidentally doing Kubernetes, and then you go like, oh, I died, but now who's responsible for it? Like there's a container breakout. Who's responsible for that? Is it because Kubernetes didn't provide the level of security that you expected? Or is it because you were just messing around with Kubernetes, didn't know how to use it, and like now it's trying to do way too much? So, in summary, we've got, for performance stuff, if you really do care about RC as a service, the seccomp stuff and limiting system calls is the most performant way of handling most of this stuff. gvisor is the like universal standard for doing this across like any cloud, any environment. I really like that as a tool, but it balances performance and security kind of in between. And if you care about security the most, that above all costs, then a hypervisor like virtual machine stuff is the solution. And that's my time. So I appreciate you listening and looking at my system call characters. I have time for questions if anybody wants to talk about my cute little characters, or they actually want to talk about containers.
So that list of CVEs you had, is that, at least based on your background and knowledge, is that more or less exhaustive, or are there more? Is that just a sample?
I feel like it's exhaustive.
Okay.
Because the takeaway for me was like there are not a lot of container breakout like CVEs. Like they're not. Like we were told in the beginning of containers, like, oh, any Linux kernel privilege escalation is going to be a CVE. It's going to all containers are going to fall over. Not really what ended up happening, right? But it's like that's kind of the list that we've seen of bugs that caused container breakout.
If you're an AWS and a CNAP shop, do you think that Fargate is the better solution than the other options that we have?
Do you care about money?
No.
Then it is. It provides really strong isolation. Firecracker is really great, and the fact that you don't have to manage it, perfect. Checks all the boxes. As long as you are willing to pay the bill and like scaling up with it, it's totally a good solution.
I'm not paying the bill.
Yeah, exactly. Cool. Appreciate your time. I'll be around. Glad to see you in Buffalo for all the out-of-towners. Thank you.